the weakest aspect of work on health, of work by health scientists, is in the degree of institutional support, which is symbolized by that small dot in the middle there. And so that makes it less feasible. However, I think that field epidemiology is well placed to find a path for institutional support and produce such badly needed health evidence of both air pollution and climate change effects on health. Next slide, please. Therefore, health studies on air pollution, on climate change, among others, can help achieve sustainable development goals and therefore help both adaptation and mitigation. And today, well, the next slide, please. We might not have the final answer that is posed by this comment in the cartoon. The question that is posed, we might not find the answer to. But we can certainly hear some experiences. Next slide. And today, we are extremely fortunate to have such well-qualified speakers from around the globe to share their work with us on air pollution and health as a window in the understanding of these complex relationships of climate change and health. And so unusually we have 4 talks today, so we have to keep to time, but following the talks, we'll have some time for discussion, a Q&A discussion, which will be moderated, but please send your questions, and Amber and Haley will help manage those questions so we can then all reflect together in the latter part of this. So I would like to introduce the first speaker, who is Dr. Tiantian Li. She is the director of the Department of Environmental Health Risk Assessment in the National Institute of Environmental Health of the Chinese Center for Disease Control and Prevention. And her major research interests include air pollution, climate change, and health. In 2014, Dr. Li won the National Special Support Program for Young Talents of China. She's published more than 100 papers in top journals and is a member of several national professional committees, including National Advisory Committee, Environment and Health Experts, and she's Executive Deputy Director of the China CDC, Key Laboratory of Environment and Human Health, and many more. And she's the Deputy Editor-in-Chief of the Journal of Environmental Hygiene. So Dr. Li, thank you very much for sharing your work with us. And please, the floor is yours.
Okay, thank you, Giovanni. Yeah. So may I share my screen? Maybe I just revise some slides, or I use this one.
I'm not sure what's best, Amber. I think we're sharing the slides you sent before, Tiantian.
Yeah, I just revise, update a little bit. May I share my screen, or I use this one? Yeah, okay.
I think you're allowed to share. I'm not sure.
Yes, okay. Can you see this? Can you see my screen?
Yes, it's not full screen yet.
Okay. Yeah, okay. Thank you so much. Yeah, I'm very honored today to be invited by the training program. Yeah, so today my topic is about the extreme weather, air quality, and health. Yeah. Sorry, here. Okay. I will start with some background of climate change, and then I will give 2 case studies. One is for heat wave, the other is air pollution. And then I will introduce our ongoing work related to the adaptation action for extreme weather. So as everyone knows, global warming is significant and changing climate. and human activity is a major driver of global warming. And the extreme event is the main characteristics of climate change. In this year, everyone knows air temperatures broke many long-standing records, and coupled with the ripple effects of climate change, which seriously affecting the human health and life on Earth. But the health impacts of the heat waves are underestimated. So this is very important. It's an urgent need to understand extreme events with the health effects. And also we need to, based on this evidence, to take the strong actions, response actions for the extreme events. So now I will give 2 examples for the extreme events with the human health. The first one is heat wave and mortality in China. This is a time series study. Yeah. So our study period is from 2013 to 2015. We include 113 counties in China. Yeah, this is a map. This is our 130 counties. And this county is located in the middle temperature zone, warm temperature zone, and the subtropical temperature zone. And we collect meteorological data, include the daily mean temperature, maximum temperature, and relative humidity. And also we collect the air pollutants, like daily PM 2.5 concentration as a confounder. And also the main important data is the mortality data. We include the daily total non-accidental mortality and cardiovascular mortality. Yeah. The definition is quite important. So here is the definitions for the heat waves. Our definition is about 2 days with temperature exceeding the county's 99 percentile of the temperature during study period. Yeah, we not only consider the heat wave effect, but also consider other heat wave characteristics effect, like the timing in the season for the first heat wave, the second heat waves, and the additional heat waves, and also the day of heat waves, the first day of the heat wave, the second and third and the fourth and the subsequent days of the heat waves. We use these statistical models. Yeah, it's a 2-stage analysis. First, we analyze the county-specific effect, and then we combine the effects using the meta-analysis. In this model, we control the relative humidity, long-term and seasonal trend, and the days of the week. These are the main results. From our table, you can see that the non-accidental mortality increased about 15% during the heat wave period compared with the non-heat wave period. And the cardiovascular mortality increased about 22% during the heat wave days compared with the non-heat wave days. And very interesting, the first heat waves in the season was associated with the greatest mortality risk. It's a quite important information. Yeah, it's about 16% for non-accidental mortality and 23% for cardiovascular mortality. And the effect size of the first to third days of the heat waves on mortality were larger than the fourth and subsequent days. Yeah, I think the most important thing to understand the first heat waves in the season, yeah, we need to take the strong actions for the first heat wave in the season every year. Yeah, this is very important. Yeah, and also we see the effects of the heat waves on mortality in different temperature zones. Yeah, for the effect of heat wave on non-accidental mortality, we see the mid-term zones has a biggest effect, and for the effect of heat wave on cardiovascular mortality, we see the warm temperature zone has the biggest effect. Generally, we can see higher latitude, higher risk. Yeah, so we need to pay more attention on the high latitude area. This is that is just the first example. Here I will give another example for the fine particulate matter pollution. This is another. This is a time stratified case crossover study. Yeah. As you all know, since 2013, our Chinese government takes strong actions for the emission reductions. So since 2013, annual PM2.5 pollution levels have decreased dramatically. You can see from these bars. Yeah. But it is still higher than global air quality guidelines of WHO. Yeah, this is the guideline, 5 microgram per cubic meter. This is our guidelines, 35 microgram per cubic meter. Yeah. So in 2020, there is a total of nearly 1,500 days for heavy pollution and extremely heavy pollution in about 300 cities in China. Yeah, you can see from these figures. So under this background, we have done study named the risk of cardiovascular hospital admission after exposure to fine particulate matter. This study from 2013 to 2017, our location is in Beijing, and we collect big data of hospital admission, including the cardiovascular diseases, MI, and other 8 cause-specific diseases for cardiovascular. And we collect the air pollutants, including the daily PM2.5 concentration. We use this PM2.5 to define the fine particle pollution events. Also, we collect ozone concentration as a confounder and also meteorological data. Generally, a total of 2 million hospital admissions were included in this study. This is the definition of heavy and extremely heavy PM2.5 pollution events. The threshold is 75 microgram per cubic meter and 115 microgram per cubic meter. We have 2 thresholds. And for the duration, I have 3. One is 1 day or more, the other is 2 days or more, and 3 days or more. So we have 3 sets of definitions. Here is the detailed information. Yeah. We use this is the statistical model. We use a time stratified analysis. So it's quite important is the stratum. This is a time stratified variables. It consists of the case ID and the same year, month, and weeks as the onset days. We also control the relative humidity and holiday. Yeah. This is the main result. The effects of heavy PM2.5 events on cardiovascular diseases. We see heavy PM2.5 pollution events and the different definitions increase the ORs of the total cardiovascular diseases, and all the ORs associated with the heavy PM2.5 pollution events lasting for 3 days or more for cardiovascular diseases were highest, which is about 8%. Yeah, increase of 8%. During the extremely PM2.5 pollution events compared with the non-pollution days. Yeah, and we see most of the specific causes of hospital admission were significantly associated with the heavy PM2.5 pollution events, all extremely heavy PM2.5 events, except for hemorrhagic stroke. Yeah. We also calculate the increased admission numbers per year, which is 1,000 and 3,000 admissions for heavy or extremely heavy PM2.5 pollution events. And from 2013 to 2017, increased additional numbers per year and increased additional days per year of heavy and extremely heavy days. Heavy PM2.5 pollution events decreased dramatically because of the improved air quality. Yeah, this is 2013 and this is 2017. Yeah, you can see this decreased dramatically. Yeah, so above 2 examples, from these 2 examples, we can confirm the relationship between extreme events and human health. So we need a response action for extreme events. This is our ongoing work. Actually, we're still working on this early warning models. So for this early warning heat health early warning model studies, we prepare the big data. Yeah, we first collect the meteorological data and then collect the mortality data and air quality data. Yeah, here, and then we construct the model. First, we have the framework, and then we use the exposure response relationship. Yeah, and then we see the heat mortality risk curve, and then we confirm the graded warning threshold. Yeah. After we have the main results, we evaluate our model. Yeah. So this is a 3-step study for heat health early warning. Yeah. This is our national heat health early warning grading threshold. We include 3 graded warning level 1, 2, 3, and also we have a pre-warning levels. So this is 4 levels early warning information. And for each of these 4 levels, we have the threshold here, and for each climate zone. Yeah. We also evaluate our heat health early warning models. Yeah. The left-hand side figure shows the frequency distribution of heat health early warning. Yeah. And the right side shows the association between heat health early warning levels with all-cause mortality, non-accidental mortality, circulatory mortality, and respiratory mortality. Our results showed, yeah, along with the levels progress, we see the mortality risk increased. So this is a very good performance for our heat health early warning models. We also use our models for the public health practice. We provide this technical approach to our local CDC, like Jinan CDC in Shandong province. Yeah, this is the information from their WeChat. Yeah, they use this model to release the early warning information this year. Yeah, for all the heat wave days. We also support the China Meteorological Administration National Extreme Weather Conservation. Yeah, this year. Meanwhile, we also developed the air quality health index. Yeah, this index, we also apply this index to our public health practice. Now, this index have been implemented in 24 pilot cities. This is the figures from different cities. Yeah, to use this index and release every day. Yeah. Finally, I would like to use this slide to conclude my talk today. Recently, we published a paper published a correspondence paper in Lancet named "The Global Need for Smart Heat Health Warning Systems." In this correspondence, we give 4 recommendations. The first one is we think we need to develop a smart population health-oriented early warning system with full coverage of heat health risk management. And the second recommendation is we need to refine the early warning system with detailed suggestion for the vulnerable population like the elder people. Yeah. And also we need to planning a compound extreme events, yeah, such as heat and ozone pollution extreme event. This is a compound during the summer. Yeah. So we need to plan this kind of heat health warning system in advance. And the last one is quite important. We need to forming a joint multi-sectoral plan of action for the early heat health risk warning management. So that's all for my talk. Thank you so much. Yeah. Okay.
Thank you very much, Dr. Tiantian Li. That was a great overview of your work and work of your colleagues in China. Many comments and questions, I'm sure, would be justified, and we'll try and capture some of that for the Q&A session at the end. So thank you again, and I would like to introduce the next speaker, who is Dr. Aishatu Abubakar Sadiq from Nigeria. Thank you. Dr. Sadiq did a PhD on environment and health engineering with a focus on air pollution and health at the University of Lyon, France. She's a consultant medical epidemiologist, senior medical officer with the Ministry of Health and Human Services of Nigeria. She has a degree in medicine and field epidemiology, and she has worked as a lead medical epidemiologist for Kaduna State in Nigeria, also as a medical officer in military and civilian health facilities, and a health researcher and visiting lecturer with Ahmadu Bello University, Kaduna State University, and the Nigeria Field Epidemiology and Laboratory Training Program. Dr. Sadiq, please.
Okay. Can you hear me? Hello?
Yes, we can hear you.
Okay, so let me repeat that. Good morning, good afternoon, and good evening, everyone. So I'll be presenting my PhD research work, which is the effect of particulate emissions from road transportation vehicles on the health of communities in rural and urban areas of Kano State, Nigeria, a comparative cross-sectional study. This multidisciplinary study was conducted in partnership with Nigerian institutions and research and academic institutions in France. Slide. These are the contents of my presentation. Slide. Airborne pollutants or particles are a mixture of different components. You can see large metropolitan cities in Paris, New York, those are in Europe, and Lagos and Kano in Nigeria, illustrating the situation. Now, there are multiple common sources of air pollutants, and the common ones we know include carbon monoxide, sulfur dioxide, hydrocarbons, and others. The main sources include manufacturing, residential, and agriculture. Transportation as a main source, it serves as a main source of volatile organic compounds, with 80% of the total particles produced from transportation as PM10s. They arise from exhaust and non-exhaust emission sources. Slide. There are mechanisms of deposition and defense, which occur in the respiratory system, which is the main organ system affected by air pollution. There are others, of course. At the upper respiratory tract, you have collision with large particle sizes greater than 10 micrometer. In the conduction zone, you have interception and sedimentation with particle sizes 1 to 10 micrometer. And distally, you have diffusion and electrostatic changes with lower size particles, which tend to diffuse into other system areas. Now, there are physical mechanisms of defense, such as sneezing and cough, ancillary action of the pseudostratified epithelium, and of course, non-physical mechanisms such as the pulmonary surfactants secreted by type 2 epithelial cells. Slide. This study combined 3 components: engineering, environment, and health. It took place in 3 local government areas or districts, depending on your country, of Kano State, Nigeria. And the 4 components were air sampling and cytotoxicity testing, a qualitative component with key informant interviews, a quantitative component with a structured standardized questionnaire, respiratory assessments, and the last component was a secondary data abstraction and review of road transportation data for 2016 to 2019. For the purpose of this presentation, I'll be concentrating on the air sampling and cytotoxicity study. If I take everything, we'll be here for an hour. Slide. Now, research questions. What are the differential characteristics of particulate emissions from road transportation vehicles in rural and urban communities? What population determinants affect respiratory health? On cytotoxicity assessment in vitro, is there a differential effect? Our specific objectives were to identify and compare the characteristics and mineropathological nature of exhaust and non-exhaust emission substances, to determine stakeholders' knowledge and perceptions, to assess cytotoxicity of particulate pollutants to macrophages in vitro, and to evaluate respiratory function and a previous history of acute and chronic respiratory disorders among residents. Slide. Nigeria is located in Western Africa. It's a highly populous country. We're one of the largest oil producing countries in the world. We're prone to heat waves, fluctuations in wind speed. We receive sporadic gusts of sub-Saharan dusts from Northern Africa, which we know locally as the harmattan. The steady state Kano has a projected population of 14.3 million. It has 44 districts and is the seat of a successful emirate. Slide. We had 12 sampling sites, 4 in each local government area. Sites R1 to R4 were located in the rural settlement, M1 to M4 in the mixed settlement, U1 to U4 in the urban, which is the municipal settlement. Now, there were variations in traffic density. We had high and low traffic density. High traffic density was characterized as the presence of greater than 30 vehicles per kilometer per hour. Low traffic density was less than that, of course. We identified pollution sources. We also measured meteorological parameters such as temperature and wind speed at each of our traffic sites. That's what you see at the bottom of the slide as the data lines. And we compared this, that's the horizontal line, to average temperatures between the period March 2015 and 2021, and also average wind speeds for the same period. Slide. The collection device was located in a portable backpack. It was developed within a collaborative partnership between 2 research institutions in France. It had a lithium-ion battery, which lasted for 4 hours because of power blackouts. That's seen in B here. In C, you can see a peristaltic pump, which was assembled within the laboratory. It was attached to a tube, which was bifurcated at the end. Each of the bifurcated ends had attached to it a filter holder, a polysulfone filter holder to obtain particles for cell culture, and a stainless steel filter holder to obtain particles for microscopy. At the bottom of the slide, you can see a schematic which shows you a magnified image of the stainless steel filter. It contains a perforated disc. It was inserted to avoid aspiration of large leaves, insects, and other organic particles. And you can see a magnified image of the carbon tabs within a sterile setting in the laboratory and saturated with particles at the distal end. We obtained our samples over a period of 2 hours and placed the sampling instrument at a height of 3 meters. We obtained more particles in Nigeria than during all our test runs within France. Slide. The particles we obtained were subjected to 2 types of analysis. We did the scanning electron microscopy, SEM-EDX, and also extracted the particles for cell culture. The SEM-EDX analysis was conducted using environmental scanning. We obtained images at different magnifications and did an analysis of the particles in terms of size and morphology, ESR parameters, using the software kaleidograph. For the particle extraction for cell culture, they were extracted under sterile conditions in France in the laboratory, dispersed in ethanol, which was subsequently evaporated, and we obtained a final particle percentage concentration of 1 microgram per microliter dissolved in ethanol. Slide. We conducted 2 types of cytotoxicity tests, the MTT assay and the DAPI assay. The MTT assay is a test of physiological activity and mitochondrial function. DAPI is a test of membrane integrity and internal aspiration of dyes into the nucleus. For the MTT assay, we use a standard protocol and finally read our absorbance in triplicate at 570 nanometers using a biotech microplate reader. We calculated site-specific means and standard deviations at 95% confidence interval. For the DAPI staining, we obtained images in a dark room to avoid denaturement and also calculated the saturated fluorescence, which is the ratio of highly intense DAPI stain cells to the total. Slide. Our results. You can see in A, the images in figure 2, saturation of the carbon adhesive disk at different sites. You can see a magnification that is in C of the saturated adhesive disk in the mixed site. In G and I at the bottom, here you can see saturation also seen at the urban site and in I at the rural site. In B, the first row, there was a large particle located in the peripheral zone, which was seen in most of the peripheral zones. There are also large particles there. In D, E, and F, we obtained silicon wicks in all our sites. And the silicon wicks showed a variation in sizes, with the largest silicon wicks obtained in the urban site and smaller ones obtained in the rural and the mixed site. At the bottom here in H, you can see fluorescent images. What you see in red are silicon containing particles, and in green, carbon-containing particles. We also calculated the ESR using a formula from a study by Schipper et al. To give us an idea of what particles were fibrillar or non-fibrillar. We interpreted the results as fibrillar particles being particles with ESRs greater than 3, 1.5 to 3 ESR were elongated particles, and those less than 1.5 using that formula were classified as round particles. For a number size distribution, that's the comparative trend diagram you see at the bottom. 51.7% of the particles were PM 2.5, with the highest number of particles in the mixed site. The mixed site is shown in gray. Slide. This is a comparison based on size and morphology using ECD and ESR, using site-specific histograms. All the histograms were skewed, with the peak number of particles obtained between 1.5 micrometer to 2.5 micrometer. These values are within the respirable fractions. Any particle that is less than 4 micrometer in diameter is a source of concern because it has the capacity to get to the distal airways and subsequently become a systemic problem. Slide. You missed one. Slide. Yes, next. Okay. So this is a comparative bar diagram that shows you particles classified as fibrillar and non-fibrillar. In all sites, non-fibrillar particles were more predominant. However, it's worthy to note that fibrillar particles shown in orange were also significantly present in all the sites, though in lower amounts. In figure 7, you can see a spectrogram, which is a mapping of elements for the large particles in the peripheral zone and the silicon wick at the bottom. And you can see peaks of elements such as iron, calcium, titanium, aluminium, and carbon. So a lot of particles were seen with different elements. Slide. This is also a classification by grouping. We grouped into 5 using the ECD and the elemental composition. And what we observed in all the sites is that the highest number of particles were in the sand category, which comprise of silicon, aluminium, iron, calcium, and others, with an ECD of greater than 1 micrometer. This was followed closely by the other particles category, which contains sulfur, silicon, molybdenum, zinc, zirconium, with an ECD of less than 1 micrometer. It's important to note that the fuel, petroleum, mined in Nigeria or processed in Nigeria is rich in sulfur. That might account for the high sulfur levels we obtained. At the bottom, you can see a bar diagram that shows you the ratio of silicon fibers to sand particles. And the highest ratio was obtained in the mixed settlement, M2. This was followed by the mixed settlement, M1. And lastly, you can also see another third in position or second, the urban settlement, U4. Slide. We did a comparison based on relative abundance of the elements and particle sizes. The scale you see, the color scale you see shows you the relative abundance. The darker the color, the more abundant. Of course, the lighter the color, the less abundance. And the most abundant elements were silicon and silicon compounds, calcium, zirconium in all the sites. And then for sizes 2.5 to 10, you can see zirconium in the mixed site and then silicon and silicon compounds in the other site. Also, we measured the distances from the households where we administered our questionnaires, which I'm not presenting today, to the points where we obtained our samples for air sampling at road traffic sites. And all the mean values, distances from sampling sites to household with residents, were less than 50 meters. The lowest value, mean plus or minus standard deviation, was obtained in the mixed settlement with a value of 34.1 plus or minus 21.7. Slide. These are the results of the cytotoxicity findings. On the DIPE assessment, the test of viability using the cell membrane and internalization of the dye, the lowest values we obtained for cytotoxicity were seen in the mixed settlement, M2, M1, and the urban settlement, U4. Now, when you look at these images in figure 11, you can see typical DIPE staining of macrophages in controlled and particle exposed conditions. The CTL, you see this is controlled, and then you can see the mixed, rural, one of the mixed, and an urban settlement. And if you just look at it, you can see that there's more intense staining with dye in the mixed settlement. However, the saturated fluorescence gave us an objective assessment. That's what we use to plot this. Now, at the bottom, you can see the results of the MTT assay for cytotoxicity, and the lowest values were also in the mixed settlements, M1, M2, and then a rural settlement, R2. To obtain a greater understanding of cytotoxicity based on traffic density, we plotted figure 13. And what we did was compare the average cytotoxicity values to traffic density, that is high or low, based on our results of MTT and DAPI assessment. And although there was greater variability in cytotoxicity values in the high traffic density sites, that's what you see in blue, as opposed to the low traffic density sites shown in red, the median values were different only on DAPI. They were almost the same on MTT. However, all these findings were insignificant. So based on our study, traffic density did not have an effect on cytotoxicity when cells were exposed to particles we obtained. So traffic density has no effect for us in this study. Slide. Now our findings are a lot. This is just a section of it. However, all our findings have been linked, not all of them, most of them, to studies obtained in other parts of the world. But this is the first time a study has obtained all these findings in one site. And to the best of our knowledge, this is the first time such a study that directly compares particles to health effects has been done in the region. The predominance of particle sizes, less than 4, have been shown in some studies globally. The mean distances to our sampling sites, which were less than 50 meters, being within a radius of maximal risk, has also been documented in some countries. Exposures within that radius affecting residents, pedestrians, and cyclists has been documented in some studies. The variability we obtained in high density, low density traffic sites, urban, rural versus mixed, have also been documented in some studies. Now, we had a high abundance of zirconium in our mixed sites. Zirconium is an element that we didn't find in France. However, in the northern part of Nigeria, there are high levels of zirconium in geological deposits. So most likely the values we obtained were linked to excavation activities, though brake parts from expended vehicles have been linked to also release of some particles of zirconium. We had fibrillar particles. Also in all our sites. And fibrillar particles have been shown to exert cytotoxicity via various mechanisms such as fragmentation. Now, it's worthy to note that we conducted this study during the dry season. Studies in other parts of the world have shown that values between dry season and rainy season or between winter and summer vary. So probably a study at another period will give different values from what we obtained. There were a lot of unpaved roads and sidewalks, especially in the rural settlement. That might account for the high level of calcium and silicon, which we obtained probably from resuspension of particles. Now, we did not calculate enrichment factors because there is no database of metal elements in Nigeria, and we were not able to conduct a deep layer soil sampling to obtain background levels, therefore enabling us to link it to the values we obtained in our study. Slide. Now, our recommendations. They are based on our findings and fortunately in line with the Sustainable Development Goals of the 2030 Agenda, particularly Goals 3, 7, 9, 11, 13, and Goal 17, which is a partnership to achieve goals, such as air pollution control. Now, they include to reduce emissions by setting up and implementing vehicle emission standards, strengthening of partnerships between regulatory agencies, increase in site-specific studies to obtain pollutant concentrations and incorporation of meteorological agencies and control strategies, greater collaboration, supervision, and funding at all levels. The first speaker who introduced highlighted this as a problem. Strengthening of vehicle import regulations at different levels, mandatory vehicle inspections and maintenance, adoption and use of alternative fuel sources, reduction of sulfur content, particularly in Nigeria, introduction of larger capacity vehicles, integration of multimodal transport plans, improved urban planning. The houses need to move there too close to the point source. Adoption and implementation of existing plans for road safety and partnerships for clean fuels, comprehensive action, intensification of public information and health warnings, increased focused research, establishment of a national air quality database and monitoring network, and also creating a repository of particle identifiers and background and metal concentrations. Slide. In conclusion, mixed settlements contain the highest proportion of PM2.5 particles. The presence of fibrillar particles with proven cytotoxicity highlights health risk in all sites. Existing silicon and aluminium-laden dust, though limited by season, serves as a confounder and worsens air quality. Our findings highlight a need for greater collaboration for focused research and mitigation and prevention strategies, the use of alternative fuel sources, improved urban planning, and of course, health education. Slide. I wish to acknowledge the following agencies, particularly the Petroleum Technology Development Fund Nigeria and the Nigerian Field Epidemiology and Laboratory Training Program. Slide. Slide. These are some of my references. Thank you. These are some of my references. Slide. Thank you for listening.
Thank you very much, Dr. Sadiq. Fascinating array of exposure science methods there. And I'm sure that there will be questions about that later. I would like to invite Professor Epi Nkama to present. Professor Nkama is a PhD, head of Environmental Occupational Health Department in the Lady Manawasa University in Lusaka, Zambia. And she's been supervising several projects on both pollution and climate change and health, and leading for the country review of all climate and health impacts in the next few years. And so also she's been a member of the faculty teaching on the advanced field epidemiology training program in Lusaka, and supervising also projects and case studies, including from participants from countries of Southern Africa, different from Zambia. So Professor Nkama, please. Thank you very much.
Thank you very much for this opportunity to share our work this afternoon on cement dust exposure and adverse respiratory health in a settlement residing near a cement factory in Chilanga, Zambia. Next slide, please. So as you've already heard, air pollution is a major public health problem. According to the WHO, World Health Organization, 7 million premature deaths annually are linked to air pollution. And the major portion of air pollution is particulate matter, which results from human activities such as cement production. So then cement factories contribute hugely to anthropogenic air pollution. We also tend to see human settlement congregating around these factories for economic reasons, thus potentially exposing such communities to dust emissions. There's been paucity of information and literature on the effects of exposure on communities. So this study investigated respiratory health effects due to exposure to cement dust. Next slide, please. We aimed to investigate the association of exposure to cement dust and respiratory ill health in a community residing near a cement factory in Chilanga, Zambia. For our study, we defined cement dust as particulate matter of aerodynamic size 2.5 and 10. So specifically, we measured season variations of PM 2.5 and PM 10 in the ambient air in the exposed and control communities over 3 climatic seasons. We also measured respiratory symptoms and lung function indices in the exposed and control communities. Next, please. The study was done in 2 communities, Freedom Compound, the exposed community, located right at the edge of a factory within 1 kilometer, and on the leeward side of the factory. The control community, known as Baulane, is located 18 kilometers from the factory. The 2 communities had similar social demographic characteristics. The difference was the exposure. So this was a cross-section study designed with a prospective panel study. A multi-stage cluster random sampling was used to select participants in the cross-sectional study. And we had 220 participants from each community who completed the survey on respiratory symptoms in the cross-section study. For the panel, a subset of 63 participants from the exposed and 55 from the control community were followed up for 3 climatic seasons from 2015, July 2015 to February 2016. Next, please. Okay. All right. So to measure the exposure, a community level monitoring station was set up in each of the 2 communities. The equipment was placed on the building rooftops at each site, as it can be seen in the picture, which allows sampling inlets to be 2 to 3 meters off the ground and away from any interference to air circulation. So I climbed on the rooftops to change 24-hour filter-based measurements of PM 2.5 and 10 daily for 2 weeks in 3 climatic seasons. We can also see on the top left, the vacuum pumps that were used to draw the air at nominal flow rate of 16.7 liters per minute using Teflon coated aluminum cyclone inlets. Next slide, please. So in this study, we had we measured 2 outcome variables: respiratory symptoms and lung function indices. We defined respiratory symptoms as any symptoms lasting not less than 2 days, and any respiratory symptom or event that required a visit to a health facility for medical assistance. We referred to acute symptoms such as cough, shortness of breath, runny nose, and sneezing. The lung function indices were measured simultaneously by medical personnel who also administered the symptom diary questionnaire. Lung function testing was performed daily using EZ1 ultrasonic flow sensing spirometer. So what we did was, before taking any measurements, the procedure was explained and demonstrated to each participant at the beginning and during each data collection period until the participant was comfortable to perform the maneuver. The measurements were done according to the American Thoracic Society standards or guidelines. So first, expiratory volume in 1 second was conducted for each participant for 14 days for 3 seasons between 7:30 to 9:30 a.m. The best percent of the sessions with 2 or more blows with reproducibility score of 4 or 6 were considered for the FEV1 and FVC. Next slide, please. So results specifically for lung function indices. So in terms of the lung function indices, there was a lower performance on all the lung indices in the exposed community compared to the control. We also observed the mean FEV1 and FVC predicted percentage for the exposed being 6 and 4 percentage points lower than the control. The lung indices were also showed season variations in both communities. Then the lowest was observed in the in dry season, as it can be seen from the slide. For the exposed community, the predicted lung function also showed minimal variations compared to the control community. Next slide, please. Okay, so then in conclusion, the ambient air of the exposed community had higher concentrations of PM 2.5 and 10. There was also significant association between PM particulate matter and respiratory health. For instance, the incidence rate of all respiratory symptoms was higher in the exposed compared to the control. The lung function indices for residents in the exposed were lower than in the control. Our study also demonstrated correlation between season variation of particulate matter and incidence rates of symptoms. There appeared to be an association between exposure to particulate matter and respiratory symptoms and lung function indices. However, I think it is important to note limitations of our study. Next slide, please. Yes, so it is important to note the limitations of our slides. Respiratory symptoms were self-reported in our study, which could have resulted into over-reporting by the study participants, especially that previously there had been publicity in the daily local papers about emissions from the cement factories. However, I should indicate that the lung function still provided an objective measure, endpoint less prone to bias, and also given the training of lung function technicians and the nature of lung function measurements that were conducted. The second limitation I could talk about is the fact that in our study, we used fixed level monitoring to measure particulate matter. This may have not captured fully the spatial and temporal heterogeneity of an individual's personal exposure due to personal behaviors and also microenvironment sources. Yeah, in addition, I think our study also did not do chemical characterization as well as source apportionment, which made it to some extent impossible to say with certainty that the source of particulate matter that was observed was cement dust. Next slide, please. However, several other elements of the study design, which was a prospective panel study, strengthen our study findings. For instance, the use of validated data collection tools such as the American Thoracic Society guidelines for symptoms and spirometry measurements. And to the best of our knowledge, this study was the first community-based to use a panel design and to demonstrate respiratory health effects. And this should serve as a baseline for future studies. Of course, the panel study design, which allowed obtaining multiple measurements over time for investigation of temporal relationship between exposure and outcome, adds to the strength of our study. Next slide, please. So, in conclusion, particulate matter increased the likelihood of suffering from respiratory symptoms and lowered lung function indices in the exposed community. With the increasing production of the use of cement, as it has been seen in Zambia, there is an urgent need for effective public health policies that aim to reduce pollution levels. And so by taking action to cut emissions and reduce vulnerabilities, cities and their citizens can gain multiple core benefits from climate action. Further works we hope to undertake include to estimate and quantify the climate change aspects of air pollution in Zambia, and also to identify priority interventions that are aimed at reducing exposure to air pollution, while at the same time they also reduce chance of climate change and its health impacts. Next slide, please. So I do wish to thank the people that I worked with on this project from the following universities: Copperbelt University, Zambia, University of Michigan, USA, and University of Pretoria, South Africa. Yeah, and I also acknowledge the background slide picture where it came from. Next slide, please. These are some of our references.
Thank you very much.
Thank you.
Thank you very much, Dr. Kama. We are running a bit late, but it was a fascinating example of field environmental epidemiology. So thanks for sharing that. We are running a bit late, so I would like to move straight to the last talk by Dr. Ariadna Curto. And Dr. Curto is a postdoctoral fellow at the Air Pollution, Urban Planning, Environment and Health Group in the Barcelona Institute for Global Health, IS Global. She is an environmental epidemiologist with extensive experience and expertise in assessment of exposure to personal, household, ambient air pollution in both high-income and low-middle-income countries. Her talk today will mainly focus on her PhD work in the context of the CHAI project funded by European Research Council and aimed at assessing cardiovascular health effects of air pollution in southern India. Please, Dr. Curto.
Okay, thanks for the introduction, Giovanni. Next. So I have divided my talk into parts. In the first part, I will talk, as Giovanni said, about the APCAPS cohort and the CHAI project based in India as part of my PhD work several years ago. And in the second part, I will focus on the ongoing data collection in the context of the PRECISE project, which is based in Mozambique, and which is part of my current research as a postdoctoral student here at IS Global. Next. So APCAPS is a prospective cohort composed of adults born in the 1987, the 90s. These children were followed up 3 times. And the data we use for the epidemiological studies you will see later comes from the 3rd follow-up. Next. So this follow-up includes the index children who were followed since birth, together with their parents and siblings. And this includes over 6,000 adults aged 18 years or older, half men, half women. Next. So the aim of APCAPS is actually to investigate the risk factors for cardiometabolic disease. So they have a comprehensive assessment of vascular outcomes. But with this figure, I would like to highlight that APCAPS also have a wide range of other health outcomes, including anthropometry measurements, lung function, and biomarkers. It was a very labor-intensive fieldwork that took 18 months to complete. And one of the peculiarities of APCAPS is that participants are spread in 28 different peri-urban villages near Hyderabad city. So there was a huge effort to set up a clinic in each of those villages so participants could attend to do all of this health assessment. But one of the limitations was that the cardiovascular and the DEXA test for bone density had to be conducted at the NIN, which is the National Institute of Nutrition in Hyderabad city. And unfortunately, even that participants were reimbursed for their time, not all of them accepted to travel there. So we could only take these tests in a subset of participants, which, as you can imagine, had an important implications for selection bias. Next. So going back to this figure, next. So later in 2015, 2016, CHAI was initiated in order to characterize long-term air pollution exposure in this UPCAPS population. Next. So the aim of CHAI was to assess the relationship between exposure to combustion particles, mainly measured as fine particulate matter or PM2.5 and black carbon, and cardiovascular risk in this UPCAPS population. Next. So then what we did in CHAI to assess air pollution exposure. So we did it at two different levels, at the ambient or outdoor level and at the personal level. At the ambient level, we developed land use regression models. So if you are not familiar with this methodology, it basically takes measurements and environmental characteristics of the area of interest to predict long-term pollutant concentrations at locations with no measurements. And with personal measurements, we did actually the same. So we predicted long-term personal exposure to all of the 6,000 adults, even we did not take measurements in all of them. Next. So here I'm going to talk about more specifically about what the measurements we did to develop the land use regression models. So for the development of the models, we choose 23 households located in 16 out of the 28 villages as fixed sites for sampling. Site selection was done to maximize contrast in several variables expected to be correlated with air pollution, which includes distance to primary roads, to the city, to industry, also household density, and also village level solid fuel use. So as you can see, most of them very GIS related. We took 24 hours PM2.5 concentrations for 21 days covering 2 seasons. And we put the pumps you can see here in the picture on household rooftops and with protective cases. These protective cases were locked for security reasons. And as a, let's say, funny anecdote, these cases were black at the beginning of the study, but then we had to paint them in white due to the high temperatures reached inside the box during the hottest months in India. Next. So what we did was to link those land use regression estimates to the home address of participants to get their long-term residential exposure to air pollution. And then with this exposure, we link to several health outcomes in UPCAPS, such as high blood pressure and prevalent hypertension, higher carotid intima media thickness, which is a surrogate of atherosclerosis, low bone mineral content and bone mineral density, and also decreased lung function. Next. Now moving to the personal level. So what we did was to put different sensors on participants, and they had to wear those for 2 sessions of 24 hours. So apart from air pollution monitors, participants also wore a camera that took a photo every 30 seconds. Photos were then processed to get an objective assessment of participants' microenvironment. So for example, here you can see in the pictures that this participant was cooking in the left picture and he was commuting in the right-hand picture. Next. So this, I want to highlight that this is not only have application to epidemiology studies, but also to exposure science studies. And here I put you as an example, this very nice study conducted by my colleague, Carles Milà, who integrated all of the data to estimate the when, where, and what. So let's say that it's the temporal patterns, the spatial patterns of personal exposure, the PM2.5, but also the what, so the predictors of personal exposure. Next. Here is a visual way to see what I'm just talking about. So this is an example of one monitoring session. So for example, in panel A, you have the temporal patterns of personal air pollution exposure. In panel B, you have the corresponding ambient concentrations. In panel C, you have one of the annotations from the camera that I was talking about. So for example, we could know at what times a participant was outdoors and at what times participant was indoors. In panel D, you also have the GPS track. So you know exactly where the participant was and at what time. And from panels E and F, you have the summary of the questions gathered through the baseline and post-monitoring questionnaires, as well as the land use regression prediction. Next. So now I'm just moving to the second part of the talk about the ongoing data collection in Mozambique in the context of PRECISE. So PRECISE is a cohort of pregnant and non-pregnant women of reproductive age in Kenya, the Gambia, and Mozambique to support research into placental disorders in sub-Saharan Africa. And it's being coordinated by a team in King's College London. So then what we have here, and in which I'm particularly involved in, is the PRECISE Home, which is an add-on study aimed to assess air pollution exposure to a subset of 200 women in the Mozambique site. So we have 100 women per site, and we are taking measurements for 5 consecutive days in 2 different points or rounds. Next. So as I focus on ambient and personal sampling before, here I'm focusing more on indoor air pollution exposure or household air pollution exposure. So what we did, we put the monitors in the cooking area and also the main living area of participants. And well, as you know, household air pollution from combustion of unclean foods is a relevant source of air pollution in most of low and middle income countries. And for this reason, we are putting also a temperature sensor, the exact, next to the main cookstove to record the number, but also the duration of the cooking events. And we also have the Apex, which is a low-cost sensor specially designed for household air pollution research. And as a reference method, we also have the UPAS, which is a filter-based sensor that is collocated with the Apex for only 24 hours. So thanks to all of this data, we are going to merge it with also personal data and ambient personal data to assess exposure with these women and linking with the placental disorders that I more in the PRECISE context. So next. So to conclude here, my just personal views after my experience doing air pollution measurements in the field. So extensive primary data collection and integration is challenging, but it's possible. I want to also highlight the pivotal role of community leaders, especially in the recruitment and engagement of participants. Also, the anticipation to extreme weather events. I just mentioned this pump overheat, but for example, yesterday there was a huge heavy windy storm in Mozambique, and then we had to stop sampling just because the households were damaged and the field workers could not go to the field because, of course, it's a vulnerable period for the people, for the local people, and then you have to leave them time and not just conduct the study. So that's something that you should take in your mind when planning field work. Also be aware of sensor limitations. And I want to also highlight here battery, because battery is one of the most important issues in low resource settings when the sources of electricity are or not reliable or inexistent. Also, I think it's very important to offer a continued training of local field workers in all aspects of field work, not only recruitment and data collection, but also data downloading, data entry, etc. And finally, even it may sound obvious, but plan field work thoroughly and do a pilot test whenever possible, just to be able to anticipate any potential obstacles. Next. And just, just thanks for your attention. And if you have any doubts, or just please feel free to contact me by email or my Twitter account. Thank you.
Thank you very much, Dr. Curto. That's a great overview there of practical, high standard environmental epidemiology in the field. So we got, of course, today we were so privileged to have 4 talks instead of the usual 3 on a difficult topic. So I think we heard about so many different aspects in these 4 topics, and we have little time for a few questions. So I like to start off with those, if that's acceptable. There was a question for Dr. Tiantian Li asking about the sources of particulate matter during the heat health risk days. Dr. Li, are you still with us?
Yes, I'm here. Yeah, I'm here.
Did you hear the question? It was about the sources of the particulate matter during the heat health risk days. You showed the matrix of different risk, and so there was some interest in the sources of the particulate matter for the higher risk days. If you could comment on that, please.
Okay. Actually, we do not monitor the components of PM 2.5, but I think most of the heavy pollution events day occurred in the winter. So maybe it's due to the coal combustion for heating in winter, I think, especially under the unfavorable meteorological conditions.
You mean for heating
I
the
think,
homes?
Yeah. I think the main source should be the combustion source from winter heating. Yeah.
Thank you.
Yeah.
That's good. So, do you also manage to include household air pollution in some of your models or your surveillance systems, or is it ambient mostly that you are modeling?
Okay. Yeah. Okay, this is a good question, actually. We just consider the ambient pollution, ambient exposure. We didn't consider the indoor exposure. Yeah, sorry, we didn't consider, but it's good. Yeah, it's a good question. Okay. Hello, Giovanni, can you hear me? Hello.
We can hear you. Can you hear me?
Okay.
Yes, we could hear your answer.
Yeah.
Thank you very much, Dr.
Okay.
Lee. That's very
Thank
kind.
You.
And then there's also a question for Dr. Sadiq. Given the results of your study, how do you support working with stakeholders and government officials? Your recommendations, how do you support them apart from this, explaining all the recommendations? That's one question. I don't know, Dr. Sadiq, if you're willing.
Yes, I'm here.
To respond, comment.
Yes, I am. Can you hear me?
Yes, very well. Okay. Thank you.
Well, we actually conducted this study as part of a research grant from the Petroleum Technology Development Fund Nigeria, which is an agency of the government. And each aspect of the study was done in partnership with government agencies, such as the Ministry of Health, the Federal Road Safety Corps, which is the regulatory agency for transportation in Nigeria, the Ministry of Environment in the home state of Kano, the FETP residents, the Field Epidemiology Program, and we also had community members involved and healthcare workers from each of the facilities. So you see, it's there are already multiple stakeholders in it.
That's good.
During our analysis and interpretation, of course, we had to give reports in the field. We had presentations and trainings. That's especially for the questionnaire, the components and the spirometry, which we didn't present here. But we were also able to, aside from the publications, we're also able to establish a partnership with the Nigerian Meteorological Agency, which is the regulatory agency for atmospheric monitoring, climate conditions, weather events. Now, they provided us with most of the satellite images we used to illustrate dust cover over the areas and relate to our own study. And a professor from that institution is also with us. We're also now in partnership with a member of the Atmospheric Research Lab. One of our graduates from the PTDF scholarship has a PhD in environmental engineering. She now works with the agency. So we have multiple governmental agencies that are involved, and other governments in other states have expressed an interest in conducting further studies and partnering. But it's important to note, let me just mention this briefly, that we have to consider the fact that conflicting priorities, especially for infectious diseases, will affect the role and commitment from the government. So we're also exploring possible private partnerships with organizations.
Well, that's very creative. And I think that there will be challenges like there are everywhere in going from one project, as you say, one funded project to a surveillance system, which is ongoing. So it's a tough challenge, but thank you for sharing your thoughts about that. I'd like to also share a question for Professor Nkama. Actually, there were several comments impressed with your bravery of doing the climbing up the ladder and placing all the equipment for monitoring PM or picking up the filters every day. So that was really remarked on. There were some questions about the lung function. Dr. Nkama, 3 questions were raised. One is whether you included children, and the other is whether you included race and gender in the stratification and analysis of the lung function values. Professor Nkama, would you like to comment? Is the
hello?
Yes,
can
yes,
you
we can
me?
hear you.
Oh, okay. In terms of the age group that was included in our study was 15 to 48. So with 15 years to 49 years old. So we didn't really include the children.
Okay, thank you.
Yes.
And what about the ethnic composition? Is it quite mixed, or is it fairly homogeneous in this population?
Well, it was heterogeneous. It was mixed.
Okay.
Yeah. So in terms of gender.
Yes, please.
Sorry, maybe I could just elaborate further. So in terms of gender, we had both male and female participants. But I should mention that there were more female participants than male.
Right.
Thank you.
Thank you very much. And I don't know if you have time for a question for Dr. Curto. There was an interest in the findings, if you have any to share, from the cooking and the vehicle that you showed in the slides.
Yeah, thank you. I just also answer through the chat to Jejosini, but
Right.
yeah, so maybe I didn't explain myself clear, but so when I put these two pictures, so these two pictures, they were taken from the wearable camera, and then it allows us to determine the microenvironment of participant, and then link this to air pollution exposure and do this kind of data integration and just develop the personal prediction models to then develop the epidemiological studies. So that's the.
Thank you very much.
Yeah.
Well, to conclude, I would suggest the panel members, the members of the working group that TEFINET set up for encouraging this work by field epidemiologists on climate and health, whether the panel members have any final remarks on the value of studying air pollution, having heard all these presentations, and what do they see as some of the way forward, having heard this. I don't know if there's any panel members willing to comment on this, or the co-benefit agenda, or the type of work that one could encourage. Carl, please. I think Carl is muted. Please, can we unmute?
Okay, thank you so much, Giovanni. Can you hear me now?
Yes, very well, thank you.
Thank you. No, I'd really like to thank the panelists. I think it's quite clear, you know, the depth and the scope of the studies that were done, and of course, the complexities of the methodology, you know, and I think this is an excellent opportunity for FETPs to have exposure, you know, to these kinds of environmental studies on air pollutants. And I think it's you know, it's just a step forward in the right direction. And I think there's opportunities for a lot more introspection and opportunities to collaborate going forward. So I see this as a step in the right direction. Thank you.
Thank you very much. And with this, I would like to again thank you all participants and speakers for sharing their time today, and the panel members. And I would like to encourage you to continue to attend this webinar series. I don't know, Amber, if you'd like to announce the next one. I think we have the 4th Wednesday of every month planned, at least for the next month, or perhaps we're skipping to the spring now. Amber.
We do have another session. It's going to be on November 30th, and we are going to be focusing on flooding, both coastal flooding and sea level. and we have a few speakers lined up. So we're really looking forward to that session. I've just placed the registration link for that session in the chat. So if you're interested in joining us, please feel free to go ahead and register. And we will be sharing out additional information across HappyNet's channels, as well as Columbia University's Global Consortium on Climate and Health Education. So thank you all for joining us today. We will also go ahead and share the slides and the recording from today's presentation with you. And you can also find those on HappyNet's YouTube channel and the Global Consortium for Global Consortium for Climate and Health Education website.
Thank you all.
Thank you. Thank you.
Bye.
Bye.